let's take a look at the linear regression t-test. The idea here is we have two variables, two numerical variables, and we plot them on a scatter plot, and we want to know if there's a linear trend in those two variables. So the question that we raise is there a significant linear relationships between those two variables? What we use to analyze a relationship is the correlation coefficient, a statistic, and we also use a scatter plot where we can visualize what the relationship looks like. So we're going to use the p-values functions package and the RStatics package here. And so you'll want to load those in. You're also going to want to load in the Medicaid data set. This is a listing of the number of Medicaid recipients by race in each of the 50 states and territories. So let's take a look at that dimensions. You see there's 76 rows, so we have some row deletion to tidy up the data set. There are only 50 states. The data set we'll be using for this example is one related to Medicaid, and the data set is the Medicaid number of Medicaid recipients by race in each of the 50 states. So we'll take a look at the dimensions of that frame. You'll see we have 76 rows, and so we'll probably have to go and delete some rows because there are only 50 states. Taking a look at that, a glimpse at that data set, you'll see under the state field where they define it as, or they the state field is the state field is named location. And so you can see the states here, Alabama, Alaska, United States is listed there as well. You can see that it looks like the white race there, the variable is the double, a numeric variable, whereas black is characters, so we'll have to address that a little bit later. It treats these as characters when they throw in the commas in there in the number thousand separators. Taking a look at this frame from the other perspective, here you see what we are looking at. So these are actual raw numbers of Medicaid recipients by race in each of the 50 states. Our problem is to determine if there's a statistically significant relationship between the number of white Medicaid recipients and the number of black Medicaid recipients as defined in this data frame. So we're going to show all the code to display the relative statistics and graphs and test statistics and p-values and so on for the hypothesis test. We'll show you the our commands you need for that. And then in the end, once we run the hypothesis test, we'll interpret what it means. The first thing we have to do is to tidy up this Medicaid frame. I'm going to call it Y from here on out. So there it is. So there it is. You can see that United States is listed there as a state. So this next line of code is going to wipe out that row. Take a look at it again. And if you take out that first row with that -1 piece in there, and then we redefine, every time we make the change, we're going to redefine to our Y frame again. Let's take a look at the tail. Oh, you can see all of this stuff down here that is not related to the data that we want. So there must be some additional stuff down here. So this next command will delete all of that stuff in the bottom. And it looked like rows 52 through 75. All right, taking a look at that. And looking at the tail, and you can see that the states stop right at Wyoming. They're the last state listed alphabetically. I'm going to change the black to a double so that we can plot the points and do Y as well. So the first thing we're going to do is to confirm or not a linear relationship exists between our two variables. The function we're going to use is core package, and our two variables are the number of Black Medicaid recipients and the number of white Medicaid recipients for each of the states. So we'll have 50 points. We might not have 50 points if we're missing some data. So we want to use only complete observations, and that's what that argument there is in the correlation command. All right, so when you run that, you can see the correlation coefficient is 0.7, which is moderately high. Once you get into 0.7, 0.8, 0.9, you're starting to see a very strong linear relationship between the two variables. The next thing we want to do with data like this is to visualize the data in a scatter plot. So we're going to go to the ggplot geom point with those two variables, and then when we run it, you can see what the scatter plot looks like. There's upward trend here, very few, no points, in fact, down in this lower triangular region. And if you go into the upper triangular region, where the hypotenuse of those triangles form this trend channel going up in this way, most of the points fall in this wide trend channel. So you can see 0.7 is the correlation, very, very strong. All right, let's put the line of best fit on that scatter plot. First thing we do is use our linear model function there with our two variables, calling data frame Y. Notice that when the output from that LM command, it gives us the most important information, the y-intercept and the slope of our line of best fit. They give us those numbers in scientific notation down here. So times 10 to the fourth, that's 10,000. So our y-intercept there is this 32,770 number. And this number over here is the slope, and it's times 10 to the -1. So if we move the decimal point one place to the left, we get the 0.433, and there's the slope. So we're going to take that line and we'll add it to the scatter plot by using the geom smooth command. We will set the standard error equal to false so it doesn't provide that shading above and below the line. Throw in a couple of other attributes. And there's our scatter plot again with the line of best fit going right through the middle. So we clearly observe a strong linear relationship, and the hypothesis test there is there to use statistics to decide in a quantitative way if the relationships, the differences, the pattern that we saw was statistically significant. So we run the hypothesis test. I'm going to redo this command here, call all of these results. So you remember those. Not a whole lot of information there. Some of those results are hidden. However, if you do the summary of the results and put those into results 2, then take a look at results 2, and you'll see that there's many more results here, unhidden. So it gives us the function that we typed in, and it computed all the residuals, difference between the data y value and what the line would predict, gets all these residuals and gives us the 5-number summary. Then here's where we need to focus on these coefficients, in particular right here. This is the t-value, which means it's the test statistic for this test. And then the number right next to it over here in the 4th column, you can see it's like a probability. It's the two-tailed probability of the hypothesis test. And this number is very close to 0. And you from some pre-established alpha level of significance of 0.05, or if your p-value is less than that 0.05, then you would reject the null hypothesis in favor of the alternative. So it's a way to systematically show support of a research hypothesis sitting down there in the alternative hypothesis. Notice this is a 2 by 4 grid, so we'll recall these numbers based on their location in the, quote unquote matrix. All right, so just a couple of these if we want to pick them out to show you how these matrix callings would occur. So in the coefficients, okay, so now we're looking at this table here, and coefficients 1, what does it give you? Well, it gives you the y-intercept of the line of best fit. Coefficients 2 gives you the slope of the line of best fit. Those are 2 numbers that you want to be able to identify and pick out from time to time. If you just say coefficients without any indication of the spot, it gives both of those to you. If you just run the coefficients frame without table frame matrix, without the numbers, then what you'll receive is that 2 by 4 table with everything labeled nicely. So we can call each of those items out of there, the standard error terms, these estimate terms, the t-value, which is the test statistic, and then the probability for each of them. We're going to focus down on the bottom 2. This one is in position, well, it's the 2nd row, and it's the 3rd column. And this one is the 2nd row of the 4th column. And so that's exactly how we would identify the number in those spots with its indices. So when we run this one, it's going to give us the number we want. Turns out to be the test statistic. And then the next one is going to be the p-value. And remember that we read p-values from right to left because they are often printed in scientific notation. So here's our p-value. It's less than our predetermined alpha, so we're going to reject the null hypothesis. Okay, well, let's take a look at what the null hypothesis would look like in this setting. Here's what it would look like. The null hypothesis would be the statement that rho is equal to 0. It looks like a P, but it'll allow me to type in Greek letters here. So rho is equal to 0, and rho is equal to the population correlation coefficient. That's equivalent to the beta being equal to 0. Now, beta is the slope of the best fit line. In layman's terms, the null hypothesis is always a statement of no difference. There's no relationship. This number doesn't equal or does equal a predetermined number that we've identified. And so the null hypothesis here is just there's no linear relationship between the 2 variables. And so the competing hypothesis to that is the alternative, which says that there is a linear relationship between the 2 variables. In this case, the number of white Medicaid recipients and the number of Black Medicaid recipients in the States. So you can see I've defined the 2 variables that I'm going to use in the hypothesis. You could really use any one of these, depending upon the author. They will say all of these, one of these two, and then they'll throw in the interpretation. Generally, we want to reject the null Generally, we want to reject the null hypothesis in favor of the alternative hypothesis, which is generally what we wanted to show at the beginning anyway. So the alternative, there is a linear relationship. And so what happened here is we rejected the null hypothesis, which means that if there's going to be evidence for one of these two hypotheses, it's not going to be the null, it's going to be the other one, the alternative. So now there's evidence in support of the alternative. Well, that's that the alternative is that the correlation coefficient is not 0, which means it's closer to 1 or closer to -1. And that means that there's a significant linear relationship between the two variables. And that's what we wanted to show. We knew it, we observed it from the scatter plot and the correlation coefficient, but we confirmed it here with this test. Ultimately, we're going to conclude a sentence so that everyone would understand, which is the claim was made that there's a relationship between these two variables. And so we assume that to be true. We went out and tested that claim empirically by collecting data, and the data shows a significant 0.7 linear correlation. And so the ultimate conclusion is that there was evidence from this test of a statistically significant direct linear relationship between the number of Black and the number of white Medicaid recipients in the states. We understand that there's a confounding variable here, and that's the state population. And our states range in population from about 500,000 up until 40 million for California. And so because of that wide variation, it's going to be the case that when you have a state that has way, way more people, they're also going to have more Black Medicaid recipients and white Medicaid recipients. So just by virtue of the fact that the populations of the states are larger, that's going to force both of those two numbers to increase at the same time, the number of Black and the number of white Medicaid recipients. Okay, so this was the linear regression t-test. So we've provided a little evidence that there's a relationship between these two variables.